So first of all, that's Rich Knight. I'm Rich Johnston, just to kind of two Riches. So yeah, we're from Arqiva, here to talk about a large project, complex project, and long project that we've been carrying out for about 4 or 5 years, something like that, on our DAB network. But before I do that, because I think there's probably going to be about 50-50 in the room who know Arqiva. I definitely see a lot of faces that I know, but definitely some young people who maybe don't know what Arqiva do. And basically, we build broadcast networks. That's what we've been doing for a really long time. Linear broadcast networks, so TV and radio. But we don't just do that. We also work in the utility space. So our smart metering network connects to 12 million households and brings back 50 million data points each day. So really what we do now is we just create complex networks capable of doing lots of data kind of going around to different places. So the DAB network's not quite as complicated as the millions and millions of sort of data points that we're doing in utilities, but it's pretty much up there. We've got about, in the company overall, we have about 1,500 transmitters. We're shipping over 400 services. And we're covering about 98% of the UK, which is a lot in terms of just linear TV and transmitters. So, anyway, back to DAB. We want to just give you some quick lessons that we learned through the process and also show a little bit about some of the conversations that have to go on between commercial and engineering, which can be interesting sometimes. And so I'll be representing commercial, and Rich is our engineer guy. So take it away, Rich.
Okay. I realised when I started to put these slides together that I'd have to explain what DAB is because not everybody in this room knows. But what I didn't think about was that in this very room are some of the experts that invented DAB. So I'm really sorry, but I'm going to compare it to a fruit smoothie. That's my plan. So if we consider a group of radio studios and the audio content that they provide as pieces of fruit, this gizmo in the middle, this thing we call a multiplexer, and that word's been used already today, is basically a fancy blender, okay? So it smushes together the bits of fruit. Smush is the proper technical term for what it does. And it creates a blend that we then distribute from a set of DAB transmitters, okay? The DAB transmitters overlap, and they transmit on the same frequency. And the blender is quite clever, okay? So one of the things that it does is it makes sure that we evenly disperse and distribute those pieces of fruit across the smoothie, okay? So that if you have a spillage, it's all right, okay? So if you lose a bit of smoothie, if you spill a little bit of smoothie, you're losing a little bit of each fruit, but you're not losing all of the banana. Okay. So DAB is very good at protecting against errors. It does that because we spread the risk across the blend of the smoothie. And this is the bit where my analogy starts to bend and creak a little bit. In the receiver, we have an unblending process. Okay. So we're going to stick with that, Rich? Yeah? Okay, an unblending process where each listener, with their receiver, they can extract the piece of fruit that they wanted. Okay. In the project that we're working on, this big piece of work, we're basically replacing the blender. We're also replacing anything on the left that's involved in collecting the bits of fruit, and we're replacing some of the equipment towards the right that gets the smoothie to the transmitters. Okay. One thing that you need to think about, or that I needed to think about, is that in those areas where the transmitters overlap with the smoothie on the right, that only works if those transmitters broadcast the exact same data at the exact same time. Okay, this is key to DAB transmission. When I say the exact same data, I'm talking about matching ones and noughts, symbol to symbol. And when I say the exact same time, those transmitters have to be synchronized to a handful of microseconds. So it's very precise stuff. Okay. The scale of the project, how many smoothies? In the UK, we have 2 national DAB multiplexes. We have D1 and SDL. We have 60 local or regional DAB multiplexes, going from Cornwall down in the southwest all the way up to the Inverness Mux in the Moray Firth right at the top there. Those multiplexes vary in size. Some of them carry 5 or 6 pieces of fruit or services. Some of them, I think we've just gone over 30. So maybe our busiest DAB multiplexer now carries 31 services. Okay. We gather 430 unique audio sources, there or thereabouts, it changes, from radio stations around the UK. And we transmit about 700. I think we got to about 702 last week, audio services. The reason those two numbers aren't the same is that it's quite common for our broadcasters to ask us to distribute one-to-many. So we get the one piece of fruit and we put it into several smoothies. Pretty common request that we get. We transmit that from 745-ish transmitters around the UK. To give you an idea of the complexity of the challenge, this was the contribution system that we were needing to replace. So this is the network that gathers the fruit. Okay, I'm sticking with the analogy. Here you can see each of these rectangles is a DAB multiplexer, so that's each of those is a smoothie. Each of these circles is a radio studio. So the blue circles at the bottom, also the green and red ones up the sides of the diagram. And this is an example system diagram from one of the studios in Fareham, quite complicated. This is the distribution network, so this is taking the multiplexer output to the transmitters. If we zoom in on the capital and look at London, each of these dotted lines is a connection from a DAB multiplexer to a transmitter, or a set of transmitters. So there's quite a lot to think about. So as engineers, it's quite tempting for us to dive straight into the technical solution. And you could get lost in here. There's a lot to think about. We found that lesson one for us was to go back to basics and zoom out a little bit from the detail and think about the big picture. Or the way I've written it here is start big and work your way towards small. Okay, so by stepping back, you can ask yourself important questions like, what is the purpose of the platform? What does it do? Not what does the old system do that you're replacing, but what does it do and who is it for? One of the examples we've got of how we stepped back from the detail and thought about the big picture and where things are happening is around the DAB compression. So in DAB, we compress the audio so that we can squeeze more bits of fruit into each smoothie, get more services onto each DAB ensemble. And we always used to do that at source, at the studio. So the DAB encoding, the compression of the audio service, took place at the studio. The multiplexing was in the centre. And that meant that the connection between the studio and the multiplexing centre is a DAB-encoded contribution service. The problem with that is there isn't really a standards-based or open protocol for distributing and controlling a DAB encoder in this way. So that was a proprietary connection. That means that at each side of that connection, you're going to have to take a solution from the same vendor. It locks you into a particular supply chain. We much preferred to move to standard open source protocols and interoperability. So we picked up the DAB encoding, we moved it into the middle. That was the basic change we made. It was pretty easy to do because bandwidth is not as expensive as it used to be, and computers are much more powerful than they used to be. So where the DAB compression is some of the heaviest lifting in this system, we were able to move that into the data center, and a computer can do an awful lot of work these days. The advantage of moving the DAB encoding into the data center is that we were able to move to a generic standards-based audio contribution service. So this is now just audio contribution delivery. There are lots of manufacturers who support that. So by applying that interoperability to the important connection between the studio and the multiplexer, we're able to effectively plug in solutions from lots of different vendors if we needed to, and it would still function. Okay. So one of the biggest challenges we faced was how on earth would we get all of these transmitters off the old platform and onto the new platform, so the way that we would migrate the system. In DAB, there are two ways of distributing the output of a multiplexer to a transmitter. There's an old-fashioned method called ETI, which stands for Ensemble Transport Interface. If you think about coaxial cables and BNC connectors, it's that kind of stuff. So whilst we had these blue boxes at the top connecting the old multiplexer to the transmitters so that we could traverse an IP network, fundamentally it's delivering ETI to the transmitters. And our transmitters, because we were not replacing them all require ETI. That's the interface that most of them need. In the new design, we wanted to move to a software solution for the multiplexing. And if you move towards software, you don't want BNC connectors and coaxial cables, you want IP connectivity. So we were going to use the distribution solution called EDI, which stands for Encapsulated DAB Interface. and that's a natively IP protocol. In order to convert it back into ETI for the transmitters, we needed this pink box in the bottom right-hand corner called an EDI to ETI converter. So we needed a method to get from the top side to the bottom side. Plan A was to manually repatch the cables. We would send engineers out to each location where we had one of those pink devices, and they'd literally pull the cable out of the old device and plug it into the new device.
Rich, it's a commercial here. That sounds like a pretty risky plan with a lot of outages. Do you think we can just do it seamlessly? Also, can you hurry up?
Okay.
That one's real too.
So Rich is right, and it's a fair challenge. We have anywhere between 2, 3, or maybe even 40 odd of these sites where we've got to do that repatching. So it would come with risk, and getting 48 engineers to do the same thing at the same time and plug all of the cables into the right position is a risky venture. So we came up with a plan B in 2 phases. Phase 1 would be to take one of those pink EDI to ETI converters and switch it around so that it's doing ETI to EDI conversion and connect that to the output of the old multiplexer. That would get us an output stream on the network that was in the correct format to bring the new device into circuit on the right-hand side in the bottom corner. And we could do that site by site. It wouldn't matter because they're all connected from the same multiplexer, from the old multiplexing system. The transmitters are getting the same content. And then the actual migration on the day would be a remote switch by resubscribing that EDI decoder from the old system to the new system. It's something that we can do remotely, which created the possibility to automate it. So we worked with some of our really talented control systems engineers, and they created a big red button for us. Okay. So we're doing lots of things at the same time, but for a human, it was quite a simple task to push the button. That big red button would drive 773 lines of code that would send an instruction to each of those 48 devices, causing them to flick across at the same time, hopefully in a synchronized fashion. Now that technically looks quite complicated, and we did start to wonder, have we traded logistical complexity, sending engineers to lots of sites, for technical complexity, which brings us on to lesson 2, the importance of testing. Okay. So the ask from engineering to the business was that we would want to invest in a fully representative test lab with all of the same building blocks that the production system would have, including the infrastructure.
Rich, fully representative sounds pretty expensive.
Yeah.
Is that really required? How are we going to justify that to the business?
Yeah, so that's another fair challenge. And it was a point of tension in the project. There's always going to be change in a system like this, whether it's how you configure the services to run over the network or potentially the network itself, firmware updates or different ways of configuring the switches and routers. So my warning back to the business was that if we didn't have somewhere to try this out, the first time you run that reconfigured service over your infrastructure or over new infrastructure would be on the production system, and it might not work.
Fair enough. Well, carry on. But, but a little bit quicker.
We've got 5 minutes. The benefit, this was arguably the best money we ever spent on the project, was building this lab. The benefit was we were able to dress rehearse the migration method. We were able to discover what mattered the most when copying the configuration from the old system onto the new system. And it turned out that some of the receivers in the field or that people have are particularly sensitive to certain things, and we had to get that right. It allowed us to find and resolve any unexpected unwanted behaviour, so that's the whole point of a test system, is to discover defects and fix them. And we learned quite a lot that we didn't know about running high availability real-time media services on cloud-based technologies. So we could talk for another 10 minutes, which won't let me, about containerization. It turns out in a containerized environment, if you're doing lots of real-time stuff at the same time, you might find the process is contending for CPU access. That was something we found quite early on we were able to fix in the lab. Lesson 3. In a long program, be ready for change. So this program has taken us about 5 years. I could argue it's been a little bit longer. It has been for me. Or maybe it's been a little bit shorter in terms of when we started to actually buy stuff and install it. But about 5 years. And in that time, the network has changed significantly. We've actually built 2 extra muxes since we started. And all of the radio stations, things have moved around a lot. Okay. So we discovered quite early on that tracking technical change is difficult. I'm sure it is for a lot of people. And that it was very important that we would identify the people and the documents that connect your old system to your new system. So in any business, and in ours this is true, you'll usually have a group of people who always find out if something changes. So for us, that was our operational staff. And once we'd identified who they were, we made sure they always told us if something changed. And then we knew where they documented all of that change. Be ready for people changes. If you run a project for 5 years, some people are going to join the business, some people are going to leave the business. Share knowledge freely, write stuff down, document your how-tos, because not everybody knows how to do everything, and do your succession planning before you need it. That was a really interesting learning point. If somebody leaves the business, you might not have time to get everything that they know into somebody else's brain or get it all written down. So do it ahead of time before you need it. And then finally, engineering priority might not always be the same as commercial priority.
Yeah, just on that, I know you've planned out the whole project and all the national muxes are going to get migrated right at the end of it. But can you just flip that entirely around so that it's just the opposite way? And can you let me know whether that's possible by midday tomorrow, something like that?
So you did let me have the test lab, so that's a fair request.
Come on.
Okay, so we did start, when we started the project, we always planned to migrate from the south to the north, but it did change when we needed to accelerate the migration of our national network. So you do always have to be ready for change. And the longer a project takes, the more stuff is going to change in the meantime. So the world doesn't wait for you while you're carrying out one of these big projects. We recorded one of the migrations. This was the very first one that we did in Northampton. This gives you a sense of what the transition was like, going from the old system to the new system. And you're not... Yes, you are getting the audio. So at the point of migration, the reception was lost. If you look in the yellow circle, you'll see it comes back a little bit quicker on one receiver than another. The actual migration of the transmission network from the old system to the new system was pretty quick. What you're hearing there is how long it takes the receiver to reacquire the signal and start to broadcast that audio subchannel again.
So a very quick wrap up. I think I don't know how impressive that last slide was. It doesn't seem that impressive necessarily. However, if you're migrating a national network with like 300 transmitters in it, 32 services, and countless like routers and switches all in the chain, it was a really sort of impressive technical feat. So hats off to Rich and the team for doing that. And then, yeah, so what we learned, back to basics. So what is your platform and what are you using it for? Don't just redesign what you've got now. Do something new if you can and think about what it's used for. Test, test, test. And in Rich's case, and in any case, any kind of company you're going to be working in, you're probably going to have to fight for budget for testing resources, and you need to be able to articulate why that's important. And just keep testing, because it doesn't matter how much you test, it's still going to go wrong. So that will happen. Change is inevitable. And then just really to finish, our program finishes in 2026, at which time all of the DAB muxes in the UK will be DAB Plus capable and on our new platform, which will be great. Thanks very much.